In this question, a symmetrical three-phase short circuit occurs on a 22 kV bus bar. So this is the 22 kV bus bar and three-phase short circuit occurs here, and we have to find out the fault current and the fault apparent power. To solve this problem, we will first make the per unit reactance diagram of the given network. The per unit reactance diagram can be drawn in this way. As you know that the generator is shown like a constant voltage source behind the reactance. So this is the reactance of the generator and this one is the internal EMF of the generator. XTF1 is the transformer number 1 reactance, XTL is the transmission line reactance, and XTF2 is the transformer number 2 reactance. This one is the bus bar number 1, this is the bus bar number 2, which is a 22 kV bus bar. And as given in the problem that the fault occurs at 22 kV bus bar, that's why I have shown here a fault. This line represents the zero power bus. This is the reference bus and the potential of this reference bus is 0 volt. Nothing is given about the load. In the problem, the examiner has not given anything about the load. So I am assuming this load to be a static load and I am ignoring this load to draw the per unit reactance diagram. Now our aim is to calculate the per unit reactance values of all the equipments of the power system network. To calculate the per unit reactance of the different equipments of the power system network, I am going to draw another diagram. So by this diagram you can easily calculate the values of the per unit reactance of the different equipments. So first we will draw vertical lines. These vertical lines will be in between the HV and LV winding of the transformers. So this one is the first vertical line which is separating the LV and HV winding of transformer number 1. This is the second vertical line which is separating the LV and HV winding of the transformer number 2. So there will be two vertical lines in this power system network. Remember, you have to draw the vertical lines first. There are two transformers, so there will be two vertical lines which will separate the LV and HV winding of the transformers. And easily you can see that in this power system network there are three sections. Section number 1, section number 2 and section number 3. Now, in the second step you have to select a common base MVA. You can take any value as a common base MVA. Here I have taken 100 MVA as a common base MVA. See, what is the meaning of the common base MVA? This is the new base MVA for all the equipments of the power system network. Now, you have to select a suitable base voltage in one of the sections of the power system network. Here I have selected 11 kV as a new base voltage in section number 1, and automatically this new base voltage will get transformed in section number 2 and in section number 3 according to the transformation ratio of transformer number 1 and transformer number 2. The transformation ratio of transformer number 1 is 132 upon 11, which is 12. So this voltage will be 11 into 12 in section number 2, which is 132 kV. Now, this 132 kV will get transformed in section number 3 according to the transformation ratio of transformer number 2. The transformation ratio of transformer number 2 is 132 upon 22, which is 6. So 132 upon 6 is the new base voltage for section number 3. Now, what is the meaning of 11 kV? The meaning of 11 kV is this 11 kV. Here you can clearly see that the range of 11 kV is from here to here. So the generator and the LV winding of transformer number 1 lies in section number 1. So the new base voltage for generator number 1 is 11 kV and the new base voltage for LV winding of transformer number 1 is 11 kV. You can see here the range of 132 kV is from this point to this point. So in this section number 2, the HV winding lies and there is a transmission line and there lies a HV winding of transformer number 2. So you can say that the new base voltage for HV winding of transformer number 1 is 132 kV, the new base voltage for transmission line is 132 kV and the new base voltage for HV winding of the transformer number 2 is 132 kV. Now you can see the range of 22 kV. This lies between this point to this point. So the equipments which lies in section number 3 is the LV winding of transformer number 2. So the new base voltage you can say for LV winding of transformer number 2 is 22 kV. Now let me ask some questions so that it can be clearly understood to you. What is the new base voltage for generator? The new base voltage for generator is 11 kV. The new base MVA for generator is 100 MVA. The old base MVA for generator is 25 MVA. The old base voltage for generator is 11 kilovolt. Now if you consider the LV winding of the transformer number 1, the old base voltage for transformer number 1 considering the LV winding is 11 kV and the new base voltage is 11 kV. The old base MVA is 30 MVA and the new base MVA is 100 MVA. If you consider the HV winding of the transformer number 1, the old base voltage is 132 kV, the new base voltage is 132 kV, the old base MVA is 30 MVA and the new base MVA is 100 MVA. Now if you consider this transmission line, the old base voltage is 132 kV because this transmission line is connected to HV side of the transformer number 1 and HV side of transformer number 2. So you can say that the old base voltage for this transmission line is 132 kV and this one is the new base voltage. New base voltage is also 132 kV. The old base MVA is 100 MVA and the new base MVA is 100 MVA. If you consider the HV winding of transformer number 2, the old base voltage is 132 kV, the new base voltage is 132 kV, the old base MVA is 5 MVA, the new base MVA is 100 MVA. If you consider the LV winding of transformer number 2, the old base voltage of transformer number 2 is 22 kV, the new base voltage is 22 kV, the old base MVA is 5 MVA and the new base MVA is 100 MVA. Now let me recall this formula. The new per unit reactance equals to old per unit reactance into new base power divided by old base power into old base voltage divided by new base voltage square. This is the formula which can convert old per unit reactances into new per unit reactances. Now we will use this formula and we will find out the per unit reactance of all the equipments of the power system network. Now we are going to find out the per unit reactance of the generator on a suitable base MVA and on a suitable base voltage. So I have already told you the formula. The new per unit reactance of the generator will be the old per unit reactance, which is 0.15, into the new base power, which is 100, divided by the old base power, which is 25, into the old base voltage 11 kV divided by the new base voltage square, and it will become 0.6 per unit. Now consider the transformer number 1. If you consider the LV winding of transformer number 1, see, the new per unit reactance of the transformer number 1 is equal to the old per unit reactance into the new base power divided by the old base power into the old base voltage divided by the new base voltage square. If you consider the HV winding of transformer number 1, you will write the equation in this way: the new per unit reactance equals to the old per unit reactance into new base power divided by old base power into the old base voltage divided by the new base voltage square, and you will get 0.3 per unit. If you consider the transmission line, I have already told you that the old base voltage for transmission line is 132 kV and the new base voltage is 132 kV. The old base power is 100 MVA and the new base power is 100 MVA. You can use this formula easily. The new per unit reactance of the transmission line equals to the old per unit reactance into the new base power divided by old base power into the old base voltage divided by the new base voltage square, and it will become 0.092 per unit. Now consider transformer number 2. The new per unit reactance of transformer number 2, considering the HV winding of the transformer number 2, is the old per unit reactance into the new base power divided by old base power into old base voltage divided by the new base voltage square, and you can write this equation in another way, considering the LV winding of the transformer number 2 in this way. See, the new per unit reactance equals to old per unit reactance into the new base power divided by old base power into the old base voltage divided by the new base voltage square, and you will get 0.4 per unit. So we have calculated the generator reactance, which is 0.6, the transformer number 1 reactance, which is 0.3 per unit, transmission line reactance, which is 0.092 per unit, and the transformer number 2 new per unit reactance is 0.4 per unit. We can put all the values in this figure. So this is the per unit reactance diagram with all the per unit values. Here, because in the question nothing is specified about the load, whether the load is static or dynamic, so I am considering this load to be static. That's why I have ignored this load, and because this load is static, that's why I have taken the internal EMF of the generator as 1∠0 per unit. All the values, the reactance value and the internal EMF of the generator is in per unit. Now see this diagram, and easily you can calculate the fault current by using the network analysis. The fault current will be 1∠0 divided by sum of all the reactances, and the fault current will be 0.718 angle minus 90 degree per unit. Now we are going to find out the fault apparent power. The fault apparent power will be V into IF. What is the meaning of this V? This V is the potential of bus bar number 2, which is 22 kV bus bar just before the fault. So just before the fault, because nothing is specified about the load, I am considering the voltage of bus bar number 2, which is 22 kV bus bar, is 1 per unit. Remember, this voltage V is the voltage of bus bar number 2 just before the fault. So just before the fault, the voltage is 1 per unit into the fault current, and you will get 0.718 per unit as a fault apparent power. See, the new base power or the new base MVA, which we have selected is 100 MVA. So the actual fault apparent power can be calculated. The actual value equals to per unit value into the base value. So the per unit value into the base value equals to 71.8 MVA is the fault apparent power. Now I want to calculate the actual fault current. To calculate the actual fault current, first calculate the base current. To find out the base current, we are going to use this formula. The base power equals to √3 base voltage into base current. Because this is a three-phase system, that's why we are using this formula. See, this base power is the new base power, and this base voltage is the new base voltage, which is 22 kV. See, the fault occurs here. The fault occurs at 22 kV bus bar. Because the fault occurs at 22 kV bus bar, in section number 3, you can see in section number 3, the fault occurs at bus bar number 2. So the new base voltage in section number 3 is 22 kV. That's why I have taken the base voltage of the section number 3 here. So this is 22 kV. So we can write the base current. The base current will be 2.624 kilo ampere, and easily we can calculate the actual fault current. The actual value equals to per unit value into the base value. See, the per unit value of the fault current is 0.718 into the base value, which is 2.624 kilo ampere, and you will get the actual fault current as 1.88 kilo ampere. In this way, we have solved this problem. There are some key points to solve this problem. To solve the three-phase short circuit problem, we need to first make the per unit reactance diagram. So to make the per unit reactance diagram, select a common base MVA and a suitable base voltage in one section of the power system network. Now the second point is regarding the load. If the load is static in nature, the example of the static load is street lights. If the load is static in nature, then during the fault it cannot feed the fault current, so you can neglect the load. And in this situation, we will take the pre-fault voltage at the faulty bus equal to 1 per unit, and the internal voltage of the generator will be considered as 1 per unit. Now the third key point is regarding the dynamic load. The example of the dynamic load is synchronous motor. Suppose there is a synchronous motor which is a dynamic load. Then during the fault, the synchronous motor will behave like a generator and it will feed the fault current, so you cannot ignore the synchronous motor. And in this situation, you need to calculate the pre-fault voltage at the faulty bus, and you need to calculate the internal voltage of the generator. And this was the third key point. Here, the examiner has not specified the load clearly, so I am assuming this load to be a static load, and therefore the pre-fault voltage at the faulty bus I have considered 1 per unit, and the internal voltage of the generator is 1 per unit. You can see here the pre-fault voltage at the faulty bus is taken as 1 per unit, and the internal voltage of the generator I have considered 1 per unit. Here I want to tell you that it is not necessary to take 100 MVA as a common base MVA. You can take any value of your choice as a common base MVA. You can see clearly that I have taken the highest rating as a common base MVA, but it is not necessary. You can take 200 MVA, 300 MVA, 400 MVA, 500 MVA as a common base MVA. one more thing. It is not necessary that you have to take 11 kilovolt as a new base voltage in section number 1. You can take 10 kilovolt, 20 kilovolt, 30 kilovolt as a new base voltage in section number 1, and automatically the voltage which you have chosen in section number 1 will get transformed in section number 2 and in section number 3 according to the transformation ratio of transformer number 1 and transformer number 2. See, when you are selecting the different common base MVA and the different value of the new base voltage, you will get different per unit value in your calculation, but in the last, when you are calculating the actual value, the answer, your answer and my answer will be same. So this was the last point, and in this way we have completed this question.